So we'll start with the next chapter. So write out the next heading as Chapter 5. Magnetism and its matter. So in the previous chapter, we were discussing about moving charges and magnetism, right? So what is the difference between the previous chapter and this magnetism that we are trying to discuss? So what do I mean by moving charges here? Means if there are charges in motion, then we can say magnetism is generated, right? So the chapter number 4 clearly tells us that as long as there is motion in charges taking place, as long as there is a motion in charge taking place, you can say magnetism is induced in the material, right? And that kind of a magnetism, we can call it as temporary magnetism, right? So we call it as temporary magnetism. Whereas if there is a question where you can have permanent magnetism existing, yes, you can say that it can have materials can have permanent magnetism also existing within them, right? So this chapter we are going to mainly deal with permanent magnets and different kinds of materials exhibiting magnetism. That is why it is called as magnetism and its matter. So is it clear? Right. Now, the next question is, when you talk about a permanent magnet, right? So when you talk about a permanent magnet, the first question that we'll ask is, where is the material obtaining magnetism from? So where is the material obtaining magnetism from? How do you say that permanent magnets are having magnetism in them only because of this reason? What is it? So what is the reason for it? It is because all materials in this world are made up of what? Yes. All materials are made up of atoms. Okay, that is the first point. When they are made up of atoms, the second point that we need to make a note is it consists of protons and electrons, means it has charges. So if you observe, Who are the charges which have the capability to move around the material? Electrons. And we know that electrons are in continuous motion. And due to this continuous motion, what is going to happen is there will be magnetism induced. So if you observe, these are all the steps that we need to understand. So all materials are made up of atoms, and mainly atoms consist of protons and electrons, where the electrons are always in continuous motion. Then what will happen is there will be a magnetism induced because these electrons are always in a continuous motion. It's not a question, actually, I asked it. So where is the material obtaining magnetism? Okay. So because of all these properties, we can say magnetism is induced in a given material. Okay. Now let's see what is going to be the value of magnetic field generated due to magnetism. Okay. So if you see, so we can call the heading as atomic view of magnetism, or you can take your textbook. So in your textbook, right, in 4th chapter, there is a topic called as atom as a magnetic dipole. See, though we are discussing it now, so there is a concept called atom as a magnetic dipole in your 4th chapter. Are you able to see the topic? You will have an electron that is given. So what is the page number? 162. In page number 162, you have the topic. What is the topic? Magnetic dipole moment of a revolving electron. So that topic, more than the 4th chapter, right? It has more relevance in the 5th chapter. So repeat the topic again. So magnetic dipole moment due to a revolving electron. Okay. So how is it going to exhibit this property? We are going to see that. Okay. Shall we get started? Now see. Let us say there is an electron which is revolving in the anti-clockwise direction, okay, with a speed v. Or you can write it as Vn also, means the electron revolving in the nth orbit. If you take it like this. Now, let's say the radius of this is r. Okay. So the next question is, first, what is my job? I need to find the magnetic dipole moment. So what is the formula for magnetic dipole moment due to a current carrying conductor? It is I into A. Correct? So it is Ni into A. If it has only one turn, you call it as I into A. Secondly, what is I equal to? I is the amount of charge flowing per unit time. Here, if you see the charge that is flowing, it is 1 electron divided by how much time does it take to complete one revolution? Capital T, one time period, right? So can I write this as E divided by what is time period equal to? Time is equal to distance divided by speed. So 2 pi r is the distance traveled with the speed of v. So this will be equal to E into V divided by 2 pi into R. Is it clear? Is that clear? Now third. So this is equal to I only. Now in the third step, I will write I is equal to E into V divided by 2 pi R. I'll multiply and divide it with M. V is the speed. Okay. And I will write, sorry, I'll multiply and divide with MR and R here. Can I do this? So this will be equal to E into MBR divided by 2 pi M into R square. Correct? Are you guys able to understand what you did? So I just multiply and divide it with R, and let me call this equation as equation number 1. Okay. Having said this, I have I is equal to E into MBR divided by 2 pi MR square. I is equal to E into MBR divided by 2 pi M into R square. But I can also say that the electrostatic force existing. Okay. Okay. I'm sorry. This is the value of current. Now what I need is magnetic dipole moment. So what is the formula for magnetic dipole moment I gave you? It is I into A, correct? So I is E into MBR divided by 2 pi MR square into area is how much? Pi R square. So R square and R square will get cancelled. Pi and pi are also lost. So can I write it as E divided by 2 pi M into, sorry, E divided by 2M into M into V into R. Can I write it like this? Right. So what is this MBR called as? What is the value MBR called as? It is called as angular momentum. Okay. Angular momentum is M into V into R. This is a concept from your 11th standard syllabus. So what I'm trying to conclude here is, if I say mu is the magnetic dipole moment, then this will be equal to E divided by 2M into MVR, or I can write it as E divided by 2M into L, because L is a symbol used for angular momentum. Is it clear? Now see, what is the direction of mu vector? Look at the way electron is revolving. So if I look at the electron, then the electron is revolving in anti-clockwise direction. So current will be in the clockwise direction. When current is in the clockwise direction, what is going to be the direction of dipole moment? So to calculate the direction of dipole moment, I told you when current is clockwise, you will have a south pole, right? So when it is south pole, the magnetic dipole moment is going to be into the plane of the paper. You need to curl the fingers of your right hand like this. So it will be into the plane. Is it clear? Okay. Now what about angular momentum? What about angular momentum's direction? Angular momentum direction is given as r vector cross p vector. Okay. So listen, r vector is in this direction, p vector is in this direction. So r vector cross p vector means you need to curl the fingers of your right hand in anti-clockwise direction. When you curl it, it will be out of the plane. So L vector is out of the plane. So what are we able to understand from here? That magnetic dipole moment is into the plane and angular momentum is out of the plane. So from this, if I write mu as a vector, then I can write it as E divided by 2m into minus L vector. What does the minus sign indicate there? That magnetic dipole moment and angular momentum, they both are always in opposite direction. Any doubt? Magnetic dipole momentum. L vector is out of the plane. Out of the plane. R vector cross P vector. You do it from your side. No? R vector is in which direction? I kappa. P vector, P is P in the actual, it is linear momentum. So P vector is in the direction of J. I cross J is how much? Okay. Up. Because whatever the direction of current, curl the fingers of your right hand in the direction. So I cross A, no, curl the fingers of your right hand and point the thumb, that will give you the direction. Okay. So basically, what is the direction of dipole moment? It is from south pole to north pole inside the magnet. So with this whole explanation, what we are trying to say is every atom will consist of magnetism because every atom is made up of electrons and electrons are going to be in continuous motion. So that is what the conclusion of this whole explanation is, right? So this is the expression you need to remember. So mu is equal to how much? E divided by 2m into L, correct? No, I've written in terms of magnitude. So E divided by 2m into L, if I take it as star, from Bohr's quantization condition, we know that from Bohr's quantization condition, we know that L is equal to n into h divided by 2 pi. Where you know this expression, where n is called as the quantum number or the orbit number, whatever you call it. What does h stand for? H is Planck's constant and 2 pi is a constant. So mu will be equal to E divided by 2m into NH divided by 2 pi. So that will be N into H into E divided by 4 pi into M. Is it clear? Right. You're done writing? Okay. If you see, mu is equal to N can vary from place to place because it depends on which orbit the electron is present. What about H? It's a constant. Charge of an electron is a constant. 4 pi is a constant, and mass of the electron is also a constant. So can I say this H into E divided by 4 pi m is a constant, and this constant is given a name called as Bohr's magneton. Okay, so where you substitute the value of H as 6.626 into 10 power minus 34 joule second. What is the charge of electron? 1.6 into 10 power minus 19 coulomb. Okay, 4 pi is 4 into 3.14, and mass of the electron is 9.1 into 10 power minus 31 kilogram. By substituting all these values, the Bohr magneton comes out to be equal to 9.27 into 10 power minus 24 ampere meter square. 9.27 into 10 power minus 24 ampere meter square. Are you guys clear? So if anybody asks you, why does a permanent magnet have magnetism? It's purely because all are made up of atoms. So if you look at the fact, then can we say we are also made up of atoms? We should also possess some magnetic property, right? Do we possess? We do possess, but the strength of the magnetic field that we possess is very, very less. Okay, so wherever atoms are there and wherever charges are moving, like how the electron is revolving in a circular orbit, magnetism can be exhibited by that material. That is what we are trying to say. Is that clear, guys? Right. So this is the first derivation that we need to understand. Which one? Bohr magneton, generally they write it as mu B. But in your textbook, there is no symbol. Okay, that is why I didn't give a symbol. You just write it as Bohr magneton. That's it. Okay, I hope it is clear, right? Now, we'll see a little bit about permanent magnets. Okay, so all these things you already know. So I'm just going to give you a little bit of theory or the history about it. So as you saw, right, the whole chapter we are going to discuss about permanent magnets. So where we'll have naturally occurring permanent magnets also. So if you see, if you go back and see the history, right, it was Thales of Miletus who was a person, who was a mathematician at that point. What he observed is, he observed that pieces of lodestone or magnetite, which is called as black iron ore, which is Fe2O3. So these materials could naturally attract iron particles. Okay, so anything that could attract iron particles, now we are calling it as magnets. Okay, then not only about them attracting the other property. See, for example, if I take this as a material where it is able to attract iron particles, if a magnet to which you connect an iron particle and keep it right, after some time, an important observation that you can do is the iron material which was there in touch with the magnet will also start exhibiting some magnetism. Because in that iron bar, what will happen is there will be small, something called as dipoles that will get arranged. Okay, we generally call it as domains. The topic is not a part of your syllabus. Okay, so there will be something called as domains, due to which there will be an alignment taking place, and the material starts acquiring some property, but that will be existing only for a smaller duration. It will not be existing for a longer duration. But still, if you observe, the important point is magnetism can be induced even to a non-magnetic substance. That is what they are trying to say. Even if a material is not magnetic, you can still induce it from a permanent magnet. Okay. Next is, later it was discovered that if you take a linear piece of lodestone and when you start suspending it freely in the air, freely in the sense when you suspend it like this. Okay, this is how the magnetic needle inside a compass will be. So if you observe it, the compass needle will actually keep oscillating like this. It will not steadily turn in this way. If you want, you can observe it. It will be somewhat like this. So why do we use a magnetic compass in the first place? Only to show the directions, right? We need to know the geographic north and the geographic south. So when you suspend it freely, it was observed that this particular lodestone could show or get aligned in a proper north-south line. Okay, and this was a property that was taken into consideration for us to have something called as a magnetic compass in today's world. So what is a magnetic compass? To obviously I told you. If you see what does a magnetic compass have? What is that needle actually? It is also a small magnet, right? So we know the fact that when a magnet is placed in the presence of external magnetic field, it starts experiencing torque. And due to the torque only, what will happen is the needle will start revolving. Are you guys able to understand this point? Yes. Next is, William Gilbert was a scientist who suggested that Earth itself started exhibiting magnetic property. That's what we call it as Earth's magnetism or terrestrial magnetism. See, for example, all our phones and everything, right? If at all you want, you can download compass in your mobile phone. When you try to place it like this, I'm not sure how many of you have checked it. Have you ever downloaded a compass? So when you place a compass, if you want to see the particular direction, right, you keep it, it will start getting deflected. How is it able to sense? Because surrounding the Earth, there is some amount of magnetism existing, and the compass needle will start reacting to that magnetism by experiencing some torque. Okay. Next is, if you see the magnetic force and magnetism, they are generally produced due to whom? Due to the electrical charges in motion. That was our first topic, I told you. So wherever you see magnetism, right, you need to make a note that materials which have electrons in motion will always exhibit magnetism. Okay. Next is, if you see, we are going to learn about artificial bar magnets. Bar magnets are not naturally occurring because no material will have a perfect shape like the bar is like the chocolate bar you will have, right? So usually the natural magnets, if you take, right, they are generally not strong magnets. So what we need to do is we need to do some changes to them to make it a better magnet, right? And secondly, what will happen is they have very odd shapes, right? So whenever you have an odd shape, it is not convenient for you in practical purposes. Generally, where do we use permanent magnets? Can you tell me some examples from fourth chapter where we are using permanent magnets? Solenoid. Solenoid is temporary magnet. We had the galvanometer, right? So in a galvanometer, what did you have? You had concave shaped permanent magnets. No? So it will not be naturally occurring. Nowhere you can go and find a concave magnet that comes. From naturally occurring, what we do is we'll give a shape to it. Okay. Similarly, there are some other points that are given here. Sorry. Yeah, there also I can use. However, if you see pieces of iron of suitable shapes, they can be made into magnets by doing what? By rubbing them against naturally occurring magnets. Because magnetism can be induced from permanent magnets to a particular material. So once you do that, it was observed that steel rod does not acquire it will acquire magnetism, but it will not acquire as easily as possible. Okay, it will not be that easy as compared to the materials like soft iron would be able to absorb it. These words are important. Okay, have this in mind. One is steel rod and the second is soft iron rod. So soft iron rod, what they generally have is they acquire magnetism very fast. They lose magnetism also very fast. Okay, whereas steel, what will happen is it will not acquire fast. Once it attains, it will have the retention for a longer duration. Okay, and that property is called as retentivity, about which we'll be learning in this chapter. Okay, it's called as retentivity. So if you want a steel rod to lose its magnetism, what we can do is we need to heat the material. Okay, one of the ways in which you can make a material lose magnetism is through the process of heating. Okay. So similarly, I told you about the soft iron and all those things, right? It will be there. Next is you need to understand what a magnetic pole represents. So what does a magnetic pole represent? So if you take a permanent magnet, right? For example, I took a bar magnet, and then this bar magnet will have what? It will have a north pole and south pole. And where will the magnetism be highest? Near the poles only, right? And these poles are called as magnetic poles. Now read. The preferred regions of attraction near the two ends of a magnet where the magnetic force due to a bar magnet is maximum. So if you observe, right, throughout the material, you can have maximum magnetic property exhibited near the ends of it. Now comes an important question here, okay, which is not there in this material. The thing is, this north pole and south pole are there, right? Are they going to exist exactly at the ends of the magnet? Or will they be slightly inside or will they be outside? They'll be slightly inside. Okay. So if you take the length from end of a magnet to another end of a magnet, you call it as geometric length. Okay. Similarly, if you take it between one pole to another pole, you call it as magnetic length. And remember, magnetic length is always less than the geometric length. Once it is, because the particles will start moving away, right? That is the logic. It has that property because of the domains concept which I told you. The domains will get aligned in such a way that it will be having the capacity to retain. Like how dielectrics are able to hold the charges for longer duration. Conductors cannot hold them because they have conductivity. Are you done?
Sir. Sir.
Yeah, tell me.
Sir, this magnetic length varies from each magnet, sir.
Yes, it depends on each magnet. The distance between geometric length also for that magnet depends on what magnet you're using. It varies from magnet to magnet. Right? So see. Now I'll be defining something called as, if you take this magnet, right? You know what is a magnetic pole, right? So now each magnetic pole will have something called as magnetic pole strength. So magnetic pole strength is generally represented by the symbol small m. Okay. And if you take the distance between the poles to be 2L, right, then this physical quantity m into 2L, that is a product of the magnetic pole strength and the distance of separation between them, is also called as magnetic dipole moment. So here you need to be careful, because for magnetic dipole moment you're learning different formulae. One is I into A. When will you use I into A? When you have a current carrying conductor, I is related to current and A is related to the area. Whereas when will you use small m into 2L? You use for permanent magnet, because permanent magnet has something called as pole strength associated with it. Okay. So how can you define it as? If I call magnetic dipole moment as mu, for example, and this is small m into 2L, then I can write small m is equal to mu divided by 2L. So can I say magnetic pole strength is defined as the magnetic dipole moment per unit magnetic length? Are you able to understand what I'm trying to say? Look at the formula. M is equal to mu divided by 2L. What is mu? Magnetic dipole moment. 2L is what? The magnetic length. Okay. So mu divided by 2L, how do you call it? I told you in physics, whatever you write in the denominator, add a prefix called unit. So can I say magnetic pole strength is defined as the magnetic dipole moment divided by, or magnetic dipole moment per unit magnetic length? That's what I do. So what will be the SI unit for it? Magnetic dipole moment is measured in terms of ampere meter square, and divided by length is measured in terms of meter, cancel it. So it is going to be ampere meter. So pole strength of a magnet is defined in terms of ampere meter. Is that clear? Now, based on this, I'm going to explain a derivation. See. Now, if I take a bar magnet, right? If I take, for that matter, a small bar magnet, okay, then what can I call this as with respect to the magnet? It's called as the axis. Correct? So if I take this point as P, right? So I have the total length to be 2L. So I'll take the center as the origin, so that this distance is L and this distance is L. Okay. And let this be the south pole and let this be the north pole. Okay. So is it clear till this step? So what I'm trying to say here is, if you have a magnetic dipole, which is a small bar magnet, then on the axis of it, right, I'm taking a small point P, which is, let's say, at a distance small a from the center of the dipole. Okay, which is at a distance small a from the center of the dipole. Then how much is this distance going to be? So it is going to be a minus L, and this distance will be, it is going to be a plus L, correct? Right? If you observe this derivation, right, is it not looking something similar to what you have already learned? What is it? So you
Electric
calculate
field due to
we calculated the electric field due to a dipole on the axial point. So what is the value that you obtained there?
4k q by r
2
cube.
into k is how much? 1 by 4 pi epsilon naught into p divided by
R cube.
r cube. So 2p divided by 4 pi epsilon naught r cube, correct? In a similar way, what do you think will be the value of magnetic field that will get generated? So 2m divided by r cube is okay. Remember, in magnetism and electrostatics, 1 by 4 pi epsilon naught is always replaced with mu naught by 4 pi. It is always replaced with mu naught divided by 4 pi. So this can be written as 2 mu naught into m divided by 4 pi r cube. Are you able to understand? That mu is different. I just gave it because I use small m there. M is magnetic pole strength, yes. In the case of electric field, it is dipole moment. Oh, sorry, yeah. I'm sorry, what you told is right. Here it is capital M. Or, yeah, there is a magnetic dipole moment. I'm sorry, what you told is right. That mu, I wrote it there not to confuse you between capital M and small m. Actually, this mu is capital M only. Because if you see in previous chapter and all, we wrote magnetic dipole moment in capital M only. Is it clear? You want me to go? No. Is there anyone also having cold? I have bad throat today. I'm not able to speak. If possible, tomorrow and day after we'll make it online. It's not this. Okay. So actually there is another derivation which I need to explain. It's a slightly big actually. So I'll just explain 2 more points for today. Okay. We'll see the remaining points tomorrow. So one point I want you to remember is magnetic poles always exist in pairs. Okay, have this in your mind. Means if you take a magnetic dipole and you try to cut it into how many other parts you want. Okay, in the transversal. In the sense, so in the transversal, not transversal, in the transversal means perpendicular to the axis. If you try to cut it, then you will have small pieces like this. So what we generally tend to think is North Pole will get split to the first part and South Pole will come to the second part, but that will not happen. What will happen? The North and South will still exist for it, and the North and South will still exist for the second piece also. Means magnetic dipoles always exist only in pairs. It means you can have something called as an isolated positive charge, isolated negative charge, but you can never have a concept of isolated North Pole or isolated South Pole. They always exist in pairs. Okay, that is one important point you need to make a note of. Okay. So apart from that, yeah, tell me. So let's say there is a big magnet. You broke it into two parts. So your doubt is what? If you put them together, you think they'll get attracted like this. Is that what you're asking? No, it will be, see, this magnet will have a north and south pole. This magnet will have a north and south pole. Now, if I try to break this again, then this will have north south pole. This will have north south. So like each. Which one? Your mask is actually blocking my ears, also blocked. Which one is north? This one is north, this is south. But only then they can get attracted, correct? Yeah. Yeah, it is still considered as north and south. Because it is like, see, it is something like a series connection. See, what happens? Suppose I have a wire of length L. Okay, I break it into 10 equal parts. Okay, let's say the resistance of the bigger wire is R. Then what is happening if I break it into 10 equal parts, and the resistance of each will be R by 10, R by 10, R by 10, right? So when you try to bring them closer to each other, what will happen to the resistance? They'll get added again. The same logic again. So what will happen is this magnet and this magnet put together, let's say it's a big magnet. It's not like they're attached. It is a bigger piece. Okay. This has certain amount of strength associated with it. Why am I calling it as strength? Because it has a pole and it has a pole here and it has a length. So it has some magnetic field associated with it. Now, when you try to break it into smaller parts, what will happen is the strength will become half. Okay. Now, imagine if this is there, no. If this is south pole, this is north pole with respect to you. Then what is the direction of magnetic dipole moment? Inside the magnet, what is the direction of magnetic dipole moment? It is from south to north, correct? When you try to break it into two parts, let's say the magnetic dipole moment for the bigger magnet was capital M. Now, when you break it into two equal parts, this will become M by 2 and this will become M by 2 so that they get added. When you try to bring them close to each other, they both will behave like a combination of a bigger magnet. So the strengths are borrowed from the bigger one. That is what it is. Cut along the horizontal plane, the pole strengths will decrease. Pole strengths will decrease. Means when you cut it along horizontal, so here we are cutting it vertical. So when you cut it along horizontal, this has a pole strength and this has a pole strength. It will become like parallel connection. You split it, no. Then half of the pole strength from here will get distributed to this one. So initially, for this amount of thickness, let's say the magnetic pole strength of this part is smaller. When you break it into half a pentagon, top part will have M by 2, bottom part will have M by 2. When you try to combine them again, these pole strengths will get added. Correct? Magnetic dipole moment does not depend upon. No, it depends. No, that's what we gave. Magnetic dipole moment is pole strength multiplied with the geometric length. No. If the length changes, it will change. Okay. Any other doubt? For which one? Inside a magnet dipole moment and magnetic dipole moment are the same time. Outside, you will not say no. Outside, magnetic dipole moment is always from south to north. And magnetic dipole moment will exist only within the magnet. Whereas magnetic field can exist outside as well. Yes. Any other question?
Sir,
Tell me.
Sir, it's not based on this lesson, sir. I had an exam in school in the first lesson, and then I have a question
Yeah, please.
from the question. Sir, it's an MCQ question. They ask which of the following process involves the principle of electrostatic induction, and the options were pollination,
1 minute.
Xerox.
1 minute. Or 1 minute. So, which of the following process will involve electrostatic? Guys, you also listen to this, okay? Which of the following involves electrostatic induction? Option number 1.
Pollination.
Sorry?
Pollination.
Spelling?
POLLI.
Okay. This is a biological term, no? Okay,
Yes,
next.
sir. Chocolate making.
Chocolate baking.
Chocolate making, sir.
Bake. Okay, chocolate bake. Okay. Making.
Yes, sir.
Uh,
And then Xerox copying.
the answer.
So, but then it's like they're saying it's pollination, and then it was it was in a book also. Yeah, I didn't understand how.
1 minute. Let me see if I'm not sure. I've not heard of it. Because Xerox machine uses first they should be a biology student. Not a biology student. How will I know? Anyway, Xerox copy actually it uses electrostatic. What is the fourth option?
So it says all of the above.
All of the above. That could also be a possible thing because when you talk about chocolate making, right? Again, it depends on in which place it is made. If it is a oven, right? Especially cakes are made in oven. So if you take that case, then I can say electromagnetic induction plays an important electromagnetic waves play an important role. See, pollination, I just read. I'm not sure. Theory of there is something called as electrostatic pollination itself. I don't know. There's something new for me. As an insect carrying an electric charge approaches a flower, charge of opposite polarity flows into the plant stem and flower and induces the electric field between the insect and the flower. I cannot explain. I will see because even I'm not a subject matter expert of it. Okay, but to my knowledge, I can say Xerox copy because see that I can explain because it's electrical part. So generally, you know how photocopies are taken, right? So when you pass in, for example, the printer that I have, right, it works on powder base. So there will be a liquid toner and there will be something like powder toner. Have you ever touched the paper which has specially come out of a machine? It will be hot, right? Why is it happening? It is getting charged in the first place, and the powder is there, right? The powder will create an impression. How is it able to exactly create an impression so that you are able to see E as an E? You don't see E as a C, right? Only if the machine is spoiled, then it will work. So when you have something, see, for example, if I take a printout of this, it should come out exactly as in the SI unit, in SI, the constant of proportionality. It cannot come out as something. My O cannot be like theta or something like that. These things have to get followed. So what will happen is there will be an electrostatic induction will be taking place, due to which the charge which is created on heating the material will actually get attached to it. The other example is if you have a room empty, right, for a few days. See, for example, you take fans also. Let's say you're cleaning this, you're dusting this week. 1 week down the line, you can observe that there will be some amount of dust still existing there. Why is it happening? Again, because of electrostatic induction. Because there will be some friction. Now, when you try to rub a material, there will be some friction. So when you're trying to clean a table, right? Let's say you're using a microfiber cloth. You rub the table, right? You're creating friction on it again, where it has a tendency to attract more of dust particles. So if you ask me, right, I'm not sure that 2 and 3 can be right answer according to me. Pollination, I'll be honest, I didn't know about it. Okay. What about chocolate making? Again, it depends on where they're making it. If it is cake, I would have 100% told you, I don't know about how chocolates are made also. Maybe I'll find out this. Any idea, da? Can you help? Chocolate, to my knowledge, again, it is made in ovens only. It is made in because you need the shape and everything, right? When you talk about an oven, that is there, but where? What is the temperature that is needed for that mold? Freeze it, no? Yeah, because you need cooling. But how you create, I'm not sure how it is created and all this. Maybe I'll read about it. That maybe I can answer by tomorrow. I'll understand at least if I read. Pollination, I can't understand. Any biology student here who can help. Okay. I don't know the answer. I have to accept it. I cannot blab or something. So if you understand, please let me know. Okay. Any other doubts, guys?
Sir, there's another question.
Yeah, please.
When a conducting soap bubble is negatively charged, then there are four options. One, the size starts varying arbitrarily.
Okay.
Second option is that it expands. Third one, it contracts. And fourth one is no change in size takes place.
Actually, it should contract because you have a negatively charged soap bubble, right?
Yes.
But negative charge, see, soap bubble is generally hollow in nature. Okay, so when you talk about a soap bubble is hollow in nature. The negative charge should go and sit on the surface of the conductor. Give me the options again.
So one, its size starts varying arbitrarily. It expands, it contracts, or no change in its size takes place.
So the electric field should get existing in this direction. To my knowledge, it's a contract. So what is given? What did they say for that? No change.
So like they were telling that because it's negatively charged, so it will repel and it will expand, something like that.
It will repel whom?
Like the charges will repel each other because of the accumulation of negative, more negative charges will repel, so it will expand, something like that. But I have actually written it contracts, sir. So
See, that depends on where they have taken the charge. But depends on what material is there beside it.
Sir,
So if you tell me that.
sir, what do you mean by its size varies arbitrarily?
Size varies arbitrarily, it will take some random shape. So generally, if you take a soap bubble, right, it is spherical in nature, no? Arbitrarily means randomly changing. Means due to the excess charge that is present on the material, wait, I'll draw and show. So this is what is called as an arbitrary change. Means it will lose its spherical structure.
Sir, since the electric field is directed towards it and the charges are at the surface, it gets a repulsive force. So this force may not be equal in magnitude, so it can take any arbitrary shape, right?
No, it will be uniformly distributed. That is not there. See, because it is similar to a spherical shell, no doubt in that it should either increase or decrease. Arbitrary shape is ruled out for that. For that, no doubt in that. But I'm only thinking, why will the radius increase? Because see, had the electrostatics part not there, then the answer is right. You know about the excess pressure present inside a soap bubble, right? 4T divided by capital R. So 4 times the surface tension divided by the radius. But here I'm only thinking which direction the force is going to act. Here also they have given it is going to increase only, but I'll check and get back on this. Okay, if they have taken the excess pressure also into consideration, then increasing makes sense. It needs to be more clear. So when you give a negative charge, according to the concept that we have discussed, what does the electrostatics of conductor tell us? Any excess charge given to the material will only go and sit on the surface of the conductor. But the explanation given here is it is just sitting inside the conductor, just below the surface of the conductor, and they are saying there is an outward force. But I have to study the theory and see. I'm not sure of what logic they are saying. According to me, it should contract only. Okay, but let me check and get back. Okay, is that clear? So that's it for today. So tomorrow we'll have an online class itself. Tomorrow and day after we'll have an online class. So yeah. Yeah. Okay. We'll give it to. Yeah, you can give. Where's we wind up?